Okay. All right. So the reason we did the last unit on Ohm's law and electrical power and current and charge and all that, so we could use it as a tool to do circuits. Yay, circuits. So we left off here yesterday, or last time I believe, we talked about AC and DC circuits, where we have direct current, where all the current travels in one direction. Positives go that way, negatives go that way. And as I say that, we need to remind ourselves that do positive charges move?
No.
No. But we, as a convention, so a convention is an important concept you understand. The convention is the bad guys can't shoot, and the hero is basically bulletproof until the very, very end. Okay, that's a convention. So by a convention, we use positive charges moving because it makes more sense for us to go from a high potential to a low potential, because charges move from high potential to low potential. But electrons are backwards, so they move in the opposite direction. Okay, so we're going to start talking about circuits today, and probably picking up after spring break. We're going to talk about circuits today. All right, so elements of circuit diagrams. When you see circuit diagrams, there's a bunch of things that you need to know what they are. So if you're like, hey, I recognize that object. So they have symbols. And by the way, a schematic is the technical name for a circuit represented with diagrams. So the big ones you need to know is this is the battery. Battery. Positive, negative, positive, negative. Do you know the difference between a salt and battery? A salt, you hit them one time. Battery, you hit them multiple times. So, yeah. And the difference between a cell and a battery is a cell is one electrochemical compartment, and a battery is several of them. Believe it or not, a 1.5. Yeah. So, this is actually not a battery. This 1.5 volt battery is actually just a single electrochemical cell. It's not a battery at all. The battery in your car is 6 cells. It's 6 2.1 volt cells. So the battery in your car is actually a battery. And depending upon how much juice your cell phone or your needs, it's either an electrochemical cell or a battery. The lithium ion reaction gives you about 3 volts. If that's all your cell phone needs, then they could actually use just an electrochemical cell. But we call everything batteries. Battery just means multiple things. Like a battery of weapons is a whole bunch of weapons. Like we have a battery of artillery. We'll fire all the guns. That's what that means, battery. Anyway, when you buy a laptop, you'll actually get to choose what type of battery you buy. You'll be like, I want to buy a 5-cell, a 9-cell, or a 15-cell battery. That's what battery means. Anyway, here's your battery. Voltmeters are usually a V with a circle around it. And voltmeters must be in series. This will make sense here in a second. Voltmeters must be in, parallel. Voltmeters must be in parallel. Parallel. Ammeters must be in series. Okay. These measure amps, and these measure volts. Voltmeters must be wired in parallel, before and after device, which we did earlier. And ammeters must be wired in series, right before or right after a device. Resistors in North America are given a squiggly line. Yeah. Resistors in North America are a squiggly line. In Asia, they're a box. It makes more sense to do the Asian way, but just so you know, there's squiggly lines in North America. The Asian way is, I think, is better because it's a box, right? You write in the box what it is. So those are the big ones. Sometimes you'll see this. This is a generator. We're going to treat generators and batteries the same way. So if you see one or the other, just realize they're both sources of electric potential. They're electron pumps. And a capacitor is sometimes shown as a line and a C, and sometimes shown as 2 lines. This is more common. This is what you find in older textbooks, but they're both capacitors. Remember how we talked about capacitors as parallel plates? So they show it as like a parallel plate.
So these signs, they're going to be used in like word problems and stuff like. Or what are the signs for?
Word problems. Yeah. So basically, when we're doing circuits, you'll have 2 types of exercises. 1, draw the circuit. 2, interpret the circuit. So you need to basically be able to look at the circuit and know that's a capacitor wired to a battery. That's a resistor wired to a battery. That's a resistor wired to a resistor wired to a battery. So that's why we really only care about these guys. We really only care about batteries and generators, capacitors and resistors, and then voltmeters and ammeters when we need to determine potential or current. Yeah.
What's the difference between the electric connection and no electric connection?
One's got a dot, but don't worry about it. Everything in this class will be connected. Basically, it's like, and one wire is going through the other side. So they're in the diagram. They look like they're connected, but they're not connected. But don't worry about it. That's you can learn use those in IEEE, industrial electrical something engineering. Because that's what it was called at Oregon State. They say IEEE. Oh, it's my IEEE class. Industrial electrical. Maybe it's like industrial electrical engineering education. That's probably what it was. Okay, anyway, double E. Other schools call it double E, just electrical engineering. All right, so those are the big parts. The battery or the generator, the voltmeter and the ammeter, and then the resistor and the capacitor. Those are the big ones. Other questions? Moving right along. All right, so I really don't care how much of this you write down because you probably already know it all anyway. So a battery is an electric pump. A resistor slows the travel of charges. A lamp or a motor is just a resistor that's actually a device. Okay? Lamps or motors or devices of any kind are resistors. So a resistor with a circle around it means that's a resistor that's also a device of some kind. Capacitor stores and releases charges, and a switch opens and closes the circuit, and a ground is basically just the negative potential battery. I think that's everything we covered. Again, if you really want to write this stuff down, then you can watch the YouTube. I want to move on. Any questions about these? You already know what those are. All right, a series circuit. A series circuit has one path for the current to flow. A series circuit has one path for the current to flow. It's water time.
Yeah.
Just put them right down there. I'll take care of them.
Okay. You have a water card on with a BC side of the card, but
Yeah. They told me about it. I don't know the details, but I'll
well, I'm the one that went and did it, so just tell me where it's under though.
Okay. Yeah. So, do you want to email me the details, or do you want Dave to email me the details?
Dave, well, because I don't do that.
Some sort of number.
All right.
Thank you. Anyway, yeah. So, a series circuit has one path for the current to flow. And everything in that path has current traveling through it at the same speed. It's kind of like this. If you had to all walk single file, you can only walk as fast as the slowest person. Make sense?
Yes.
And if somebody in the path stops, everybody stops. Okay? Because you're moving single file. That's how current in a series circuit works. Everything is connected one after another. If any place the current stops everywhere. This used to be used in old Christmas lights because they were cheap. If any of the Christmas lights burned out, the whole strand burned out. they don't really do that anymore because they realize little pieces of metal to make that stop happening isn't really very expensive. But series circuits are valuable in one place. Can you think of a situation in your life where you would want a circuit that if any device failed, the whole circuit failed?
Traffic?
Mm,
Like cars?
You're getting there, but the analogy for cars, we'll use the analogy for traffic very soon. Yeah.
The nuclear reactor.
Nuclear reactor.
Well, I know it doesn't
In your life, can you think of a device?
I got
Yeah.
a roller coaster.
In your life, you think of a situation where if any object in the circuit failed, the whole circuit failed.
Oh, breaker.
A breaker, exactly. Breakers and fuses. Breakers and fuses are wired in series because if any part of the circuit fails, you want the whole circuit to fail. So you've all done like something along these lines where you plugged in too many things and the whole wall turned off.
Yeah.
GFCIs, ground fault circuit interrupters, also do this. If you drop your toaster in the bathtub, your GFI will pop and your whole bathroom will turn off, just in case.
And you'll die.
No, you'll be okay.
You would be okay.
That's what the GFCI is there for. Unless your GFCI failed, the GFCI is basically there to kill the power if there's a sudden spike up or down.
In all the movies, they put like this toaster in that balcony.
Yeah, like in Groundhog Day. Well, obviously that was not wired to code. That bathroom was not wired. Your houses are all wired to code, where you have to have a GFCI even where there's water. Question?
I was gonna say, what if you're in the bathtub?
That's the
You're fine. Yeah.
So you're saying you should try it?
It's your homework tonight.
Mom, it's class.
Okay. Also in your cars, if there's an electrical spike in your car somewhere, you want that circuit to be blown out because a little fuse costs about $1.50. Your headlights cost a couple $100. Your wiring harness and your electrical computer in your car costs several $1,000s. So if there's a spike somewhere in your car, you want that fuse to blow out so all the current just stops. It's better to like, oh no, I have to get a tow truck, $50. Instead of, oh no, I have to rewire my entire wiring harness, $5,000. So your fuses and your breakers are wired in series. Now parallel circuits have multiple paths. Multiple independent paths that all have the same access to the voltage source. Your house is wired in parallel. The fuses are wired in series, but your house is in general wired in parallel. Which is good, because it'd be really strange if you had to run your toaster to run your blender. Or if you had to turn your bathroom lights on in order to shave, just because you're like, turn lights on food. So I guess your legs. Yeah. And
In a parallel circuit, what did you say they all have access to?
they all have the same access to the voltage source.
Okay.
Let me show what I mean by that. This light and this resistor, they have access to the voltage source, and this light and this resistor have access to the voltage source. They both have, each branch has independent access to the voltage source. As far as this light is concerned, it only cares about this resistor and this voltage source. It doesn't care what's going on in any other branch. Each branch is independent of any other branch. So, all the circuits in your house, they're all wired in parallel. Each of the outlets is wired in parallel. Then it's all wired down into series with the breaker, but the individual outlets are wired in parallel. Okay, so let's talk about speed. Heidi's example of a freeway is an excellent one. If you have one lane of traffic, all the traffic can only go as fast as the slowest car. In a parallel circuit, you have multiple lanes. So each lane can travel at different speeds. This branch can have a different current than this branch. Does that make sense? Because this branch is independent of this branch. But everything in this branch has to have exactly the same current. If there's 1 amp through that light, how much is through that light? 1 amp. How much of that resistor? How much of that resistor? How much of that battery? 1 amp. It's 1 amp, 1 amp. In a series circuit, write this down, current is constant. Or the same, I guess would be best. In a series circuit, current is the same. It has to be. They're all one lane. One lane of travel. All the electrons are only going as fast as the slowest electron. In a parallel circuit, each branch can have a different current. In a parallel circuit, each branch can have a different current.
And by that you mean current speed, right?
Flow of charge, yeah. Current is flow of charge. You can think of it as speed of the electrons. Okay, that's current. Now let's talk about potential. Is it okay if I say voltage from here on out?
Yes.
Okay. In a series circuit, each device shares the total voltage. In a series circuit, each device shares the total voltage. And if this is a little foggy, that's okay. We'll do lots of examples. In a series circuit, each device shares the total voltage. Now what does that mean? If this resistor gets 2 volts, and this resistor gets 3 volts, and this light gets 4 volts, and this light gets 4 volts, that means the battery is pumping out 13 volts.
That's just the total of all.
Yep. The battery is the total of all the voltages in each individual device. As long as you realize it is the battery that's producing the voltage, not the device that's producing the voltage. So the total voltage in the battery is divided amongst each individual device. According to the equation, V equals IR. According to that equation, the battery gets 13 volts, produces 13 volts, it's going to be divided amongst each individual device.
So you could say that all the voltages of that circuit are a function of the current, or
Current and the
where
resistance.
Where does resistance play into that? Is that just like what is making the voltage?
We're going to get to it. Yeah, we're going to get to it. So we're going to use this equation to find out how we can determine the current and the voltage and the resistance in each individual device.
Right.
But we're not quite there yet, but we will be soon. Okay, so in a series circuit, the current is the same, and the voltage is divided amongst individual devices. The total battery voltage is the voltage from each device. Boom, 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 boom. Okay, cool? Give me a thumbs up, that makes sense. Okay. If that makes sense, what can you say about the voltage in each branch in a parallel circuit? If this battery is pumping out 12 volts, what's the voltage going into this branch? Question? Or answer?
Is each branch going to have 12 volts in it then?
Yes. Yep. Because each branch has independent access to the battery. So if the battery is pumping out 12 volts, this branch is going to grab 12 volts, this branch is going to grab 12 volts.
Wait, if that battery only has 12 volts, how is it pulling 24 total? Is it because it's all one circuit?
It's because each branch has independent access to the battery. It's kind of like this. Imagine you had a 100-foot cliff, and water was going over that 100-foot cliff. Would it matter how wide you're going to put a paddle wheel in that waterfall to get energy from it? Would it matter how wide the waterfall is?
Yes.
Or would it matter if that waterfall split off? It actually doesn't, because all you're looking at is your water wheel. It doesn't matter if somebody else put another water wheel right next to you. Does that make sense? My analogy is a little shaky, but you get the idea. So, I hope. So, this branch has access to the battery at 12 volts. This branch also has access to the battery at 12 volts. What you're concerned about is energy. And when we get to energy, then we'll talk about realizing, oh wow, another branch means you're going to have to pump out twice as much energy. But right now, all we care about is potential voltage. Okay, does that make sense? Now, if that does make sense, realize in my drawing here, if this light has 4 volts through it, then this resistor must have what? 8 volts. Because this is in series. And if this resistor has 6 volts, then this light must get
6 volts.
6 volts. Are we good? All right. So that's level 1. Level 1 done. Okay. No questions? All right. You will have some eventually. That's all right. Other important devices, ammeters and voltmeters. Right. So I talked briefly about ammeters and voltmeters a while back. In ammeter, you're going to put in series. A voltmeter, you're going to put in parallel. You wire them like this. Depending on your target device. Oh wow. You really can't see that when it's so small. Oh, well. This is a bus fuse that's being shorted out. You can't see it unless you're really squinting through it. You can see how it breaks in the middle. This is what happens in your car. Can you see it?
Sort of under ammeter, that first bullet point, it says device that monitors the what through?
Current through. The device that monitors the
Oh, there's
current
another
through
one there. Okay.
circuit. So we say voltage drop across and current through. And that's just an animated GIF file picked up offline. It's a bus fuse like the fuses you have in your car. They shorted it out, and you can see the little metal thing melt as they shorted it out. I couldn't even see it until I realized. Oh. And once again, we talked about fuses. Fuses are things that, if you overload them, they just melt. A breaker is something, if you overload it, it throws a spring and opens the circuit. We use solid, unreplaceable fuses, or sorry, solid replaceable fuses in your car, because the idea is if your car gets a spike, the fuse blows, and you drive it to a mechanic, and they're like, "Oh, we can fix that." They don't trust you. Just like, "Oh, my radio blew out. Click, working again."
Or in what? Maybe put it or a breaker.
Yeah. A breaker is what you have in your house, and it can be reset. Those little black boxes and the big gray box with the metal door and the little boxes inside, they go clunk clunk. Those are the breakers. Little fuses are in a fuse box. Some of your fuses are under your hood, and some fuses are near your left knee. What the fuse boxes? The big fuses are under the hood, and the little fuses are next to your left knee. If you don't know where your fuse box is, you should probably find out. Save yourself hundreds of dollars. Okay, moving right along. Moving right along. Kirchhoff's rules. Kirchhoff's rules are basically what we've just talked about. There are 2 of them. You need to know what they are, because it's kind of like saying F equals ma is Newton's second law. Inertia is Newton's first law. Well, inertia is what happens, and Newton's second law is what we name. You're like just basically a shorthand. We'll name it after that guy. Kirchhoff's, same kind of thing. Kirchhoff's rules are what actually happened. Like, we're just going to name after that one. Rule number 1. The total voltage exiting the battery must equal the total voltage in all the devices. Gesundheit, I guess. And that's what we talk about. That's Kirchhoff's rule number 1. If you got total voltage in the battery, that total voltage needs to be exhausted in all the devices.
So when it says in each element, that just means devices?
Yeah. So by example, let's just go with our simple 12-volt battery. If a 12-volt battery is 12 volts, that means it's plus 12 on one side and 0 on the other. It has 12 volts of potential. The cliff is 12 volts high. The water's going over. So if you got a 12-volt battery and you lose 4 here, that means there's 8 left. And you lose 2 here, that means there's 6 left. Which means this V3 better be what? 6. So it has to have 0 left. Okay. It has to go in with 12. Go into the devices with 12, come out of the devices with